We now examine Newton's third law. Newton's third law typically plays a less prominent role compared to the first and especially the second law, but what we'll see is that understanding Newton's third law can be key to analyzing situations where there are multiple forces acting. So let's look at Newton's third law. Here you can see the statement of the law, and what it describes is the interaction of forces between two objects. And what it says is that if one object exerts a force on a second object, then that second object exerts a force back, which is equal in size, but in the opposite direction. The two forces described in this law are called action-reaction pairs, and it will occasionally be necessary to understand where the pair is located when analyzing forces on multiple objects. The first force in the pair is called the action force, and the second force in the pair is called the reaction force. So you've probably heard Newton's third law described in terms of these action and reaction forces. And the way it is often described is, for every action, there is an equal and opposite reaction. Let's look at how this comes up in an example. In this example, we're asked to draw some free body diagrams and then ultimately identify the action-reaction pairs. We'll start by drawing a picture. Here's the ground with the table sitting on top of it, and then my box sitting on the table. Nothing fancy, but at least it illustrates the relevant pieces of information. In part A, I'm asked to draw a free body diagram for the box, and then in part B, I'll be asked to draw a free body diagram for the desk. Let's look at the box. I first draw the force of gravity acting on it. Because the mass is 5 kilograms, the force of gravity is 49 newtons. It's not moving, and so there is also a normal force, and that normal force is 49 newtons as well. Now let's look at the desk. The desk has a force of gravity acting on it, and because its mass is 30 kilograms, the force of gravity is 294 newtons. Because the box is sitting on the desk, it also exerts a downwards force on the desk, and in this case, it is equal to 49 newtons. There's also a normal force from the ground pushing up on the desk, and that's going to have to cancel out both these downward forces, so it has a magnitude of 343 newtons. So now that we've drawn free body diagrams for both the box and the desk, let's look at the action-reaction pairs. And so students are often surprised that if we look at these free body diagrams, there is only one action-reaction pair. And that action-reaction pair has to do with the normal force acting on the box. Can you identify its reaction? Students are often surprised that the reaction force is the force acting by the box down on the desk. And they're surprised because they want it to be the force of gravity because they know the force of gravity cancels with the normal force. But gravity and the normal force are not action-reaction pairs. It's very important, and I'll discuss that in just a minute. So one way to make sure that you're identifying action-reaction forces correctly is to write them out in a sentence. So let me write the normal force out in a sentence. The normal force is the force of the desk pushing up on the box. And so to identify its reaction force, I highlight three important things in this sentence: the box, the direction up, and the desk. And to find its reaction force, I reverse the order of the objects, and I change up to down. So let's see what that sentence looks like. Now the sentence reads, the force of the box pushing down on the desk. And so you can see that the two forces I circled in green are these action-reaction forces. So let's talk more about the force of gravity acting on the box. In this case, I'm going to write down that force in a sentence. This is the force of the earth pulling down on the box. And by rewriting that sentence in the same way I did before, I can find its reaction force. And so this is the force of the box pulling up on the earth. And so that's often quite surprising, and we will discuss gravity more. But what you see here is that yes, the earth pulls down on you, but you also pull up on the earth. And so where is the reaction force to the force circled in purple? Well, we would have to draw a free body diagram for the earth, and it would be located on that free body diagram. We can look at the normal force on the desk and identify its reaction force. Well, let's write it out in a sentence. The normal force on the desk is simply the force of the ground pushing up on the desk. And so rewriting that sentence, we can identify its reaction force. That's the force of the desk pushing down on the ground. And so in this case, we would have to draw a free body diagram for the ground or the floor or whatever the desk is sitting on. And in that free body diagram, we would be able to identify its reaction force. And so one of the key things here is that action and reaction forces almost never occur in the same free body diagram. Even here, you can see that the only action-reaction pair that we had was one force in the box's free body diagram and one force in the desk's free body diagram. It's very rare that the two forces will show up in the same free body diagram, and we'll see that more in an example that we'll study in just a minute. In this example, we're just going to be examining Allison, who's walking across the floor. But by doing so, we'll understand the importance of these action-reaction forces. And so there are some simple questions here. If Allison's walking to the right, well, what direction is she pushing her foot? In what direction does she move? And what force causes that movement? So let's go ahead and look at this in a little more detail. Now, I just draw a simple picture here to illustrate it. And so in part A, what you realize is that if you're ever trying to walk to the right, you push your foot to the left. And so the question is, how does this pushing to the left cause your body to go to the right? Well, the point is that the direction you move is to the right, but the force that causes that, well, let's look at it in a free body diagram. So here's a free body diagram for Allison, and here's a free body diagram for the ground. Now, Allison has vertical forces acting on her, gravity and the normal force, but we're not really concerned about those in this situation. The point is that the force that allows her to move to the right is the force of friction. And the force that she's applying actually acts on the ground. And so this makes sense because the only things that cause an acceleration on an object are forces that act on that object. And the leftward force that Allison is pushing with doesn't act on her, it acts on the ground. And what she's counting on is a reaction force due to friction to cause her to move to the right. And so we can see that these action-reaction forces arise all the time. Let's look at another example. This one will examine more action-reaction pairs. In this case, what we're examining is a simple situation of Ryan opening a door. And so Ryan pulls on the door to open it, and the question is, what is the reaction force to the one that Ryan is supplying? Well, if Ryan pulls on the handle of the door, then the handle pulls back on Ryan. And so just as in Newton's third law, there are two forces, same magnitude and opposite direction. Part B is getting at the question, why do these forces not cancel? And we talked about that in a previous example, where we said the reason they don't cancel is that they act on different objects. Ryan pulls on the handle, and that force acts on the handle. The handle pulls back on Ryan, and that force acts on Ryan. And two forces that do not act on the same object, and therefore are not contained in the same free body diagram, cannot possibly cancel. And so that is why there is no cancellation here. We just have two forces in opposite directions acting on separate free body diagrams. Let's apply all this to a problem where we actually have to calculate the motion of an object. In this case, what we see is there are two boxes, A and B, and a boy is pushing on A, and that's causing both boxes to slide across the floor. And so what we want to do is find out the acceleration of them, the action-reaction forces acting between them, as well as how far they move in 3 seconds. Well, we start like we always do with the picture. Fortunately, in this case, it's given to us. Now we draw our origin and coordinate system. I let the origin be where the boxes are originally located, and I let my x-axis point to the right and my y-axis point upwards. Now I want to go ahead and draw free body diagrams. I'll need to draw a free body diagram for A and a free body diagram for B. Let's start by looking at A. Again, there's a force of gravity acting on A, and because its mass is 3, that force of gravity is 29.4 newtons. There's also a normal force acting upwards on A, and because it's not moving up or down, then we know that normal force is 29.4 newtons as well. There's the force that the boy is exerting on box A, and as it says in the problem, that push has a size of 40 newtons. There's also the force that B is going to exert back on A, and we don't know the size of that yet, but let's label it FBA. Now let's look at the free body diagram for B. It also has a force of gravity, and because its mass is 5 kilograms, that force of gravity is 49 newtons. The normal force cancels out gravity in this case and also has a size of 49 newtons. And then there's just one horizontal force acting on B, and that's the force of A pushing on it. And so let's label that FAB. Now, oftentimes students think, oh, well, the boy's pushing, and that is causing the box B to move. Shouldn't I be drawing that on this free body diagram? But if you go back to one of our tips, if it's not touching, it's not acting. And in this case, the boy is not touching box B. And so B will move, but what's going to be causing it to move is the action-reaction force that acts between A and B, not the boy's push directly. And we'll see that in just a second. So let's continue with our problem solving. Let's write out Newton's second law. We don't need to worry about the vertical directions anymore. So let's look at Newton's second law for box A, and we'll also need to write down Newton's second law for box B. We start plugging in our values for box A, and there's the force of the push, which is in the positive direction, and then there's the force of B on A, which is in the negative direction, and this is equal to 3 times A. We can simplify this just a little bit to plug in the value for the push, and we get 40 minus F of BA equals 3A. Now let's look at box B. Box B only has one force, force of A on B, and it acts in the positive direction, and that's equal to 5A. So ultimately what we see here is a system of two linear equations, and we want to be able to solve. The problem is the way it's written is there are three unknowns, FAB, FBA, and then the acceleration. But we know because of Newton's third law that F of BA equals F of AB. They have the same magnitude. That's what Newton's third law says. And so really, those two are the same value. We could call it F. Therefore, we can solve this system of equations by substitution. And so we go ahead and substitute them in, and we get 40 minus 5A, which is the force of A on B, is equal to 3A. We simplify that to give 40 equals 8A. It's worth pausing to examine this step because it tells us what we knew all along, that the 40 newtons that the boy is pushing with are causing this full 8 kilogram object to accelerate, and that's what this is saying here. 40 is equal to 8A. We then solve for the acceleration, and that gives us 5 meters per second squared. And so now we know the acceleration, and this is the acceleration of both blocks because they move together. To solve for part B, we simply use one of our equations. F of AB is equal to 5A. We plug in this acceleration to find that the force acting in between them is 25 newtons. Finally, in part C, we're going to continue our problem solving, trying to describe the motion of this object. In this case, we need to write down our kinematic variables in the x direction. The acceleration is 5 meters per second squared. The initial velocity is 0 meters per second, and the initial position is 0. Our question is, what is x when t equals 3 seconds? And it should be clear that because this is time and position, we should use the first kinematic equation. We write that out, plug in our values, and then we can solve and arrive at 22.5 meters. We finally finish by writing our answer in a sentence and say the boxes move 22.5 meters.